Good morning, everyone, and thank you to Dr. Kaplan for inviting me to speak today. I'm really excited to be back here at Phelps Lab to talk to you about my experience working as a wetland scientist for the St. Johns River Water Management District. Before I get started on our Whirlwind tour, I want to give you a little bit of background. For a little personal background, I started out at the Florida Atlantic University in the pre-med program, and I had a zoology major. But when I started taking plant classes like plant taxonomy and physiology, I became enamored with plants. And then nearing graduation, I found out that the South Florida Water Management District was looking for an entry-level scientist to work in the Everglades. So I jumped at the chance to work in the field of wetland science. However, after 2 years of working for South Florida, I moved to the St. Johns River Water Management District so that I could go back to school at UF and get my graduate degree in wetlands ecology. I was a grad student at the same time as Dr. Mark Clark. Now a little background on the water management districts. There are 5 in the state of Florida, established in 1972. The South Florida Water Management District is located in the southern end of the state, and it includes systems like the Kissimmee River, Lake Okeechobee, and the Everglades. The St. Johns River Water Management District is located in northeast and east central Florida, and this includes the St. Johns River, which is the only north-flowing river in Florida, and that's going to be the location of the wetland work I'm going to talk to you about today. At the district, we have 4 core missions. They are flood protection, water supply, water quality, and finally, what I do at the district focuses on the natural systems component. There's a great diversity of ecosystems, of habitat types ranging across the landscape from uplands to wetlands. However, wetlands are the most abundant natural ecosystem in district-owned lands due to its position on the floodplain. And that's where my work comes in with wetland restoration, hydrologic management, and invasive species management. And I want to make an important point that in all our endeavors at the district, we use actionable research or investigations that are designed to better understand wetland ecosystem processes. These then serve as the basis for us implementing these science-based management strategies. And as we monitor the results of our actions, we adaptively manage to achieve the desired outcome. Most of my career at the district has been focused in the upper St. Johns River Basin at the headwaters of the St. Johns River. In the early years, I was involved in the restoration of floodplain wetlands, and then since that time, I've mostly participated in large-scale ecological studies to implement those science-based management strategies we talked about. Again, everything must have a management focus. For each example on the Whirlwind tour, and it is going to be fast, I will tell you the issue at hand, our approach for investigating those solutions, the results of the investigations, and the application of that information to management. So let's get started with some work we did looking at sawgrass and cattail that was presented at the 2000 meeting of the Society of Wetland Scientists in Canada. Sawgrass is the historically dominant species of the Everglades and Everglades type marshes in the upper basin. The issue was because of anthropogenic impacts to water quality, fire regimes, and hydrologic regimes, sawgrass marshes were being replaced by cattail that's known to expand in areas of higher nutrient inputs, and by willow, known to encroach where water levels are lower and where there's been less frequent fire. In the Blue Cypress Marsh Conservation Area, which we'll talk about a lot today, there's been a recent increase in willow and cattail adjacent to areas of disturbance. Willow invaded from the southern and eastern boundary along State Route 60 and the L77 levee, and cattail invaded from the western boundary at an area of historical nutrient input. However, the majority of the Blue Cypress Marsh is oligotrophic and one of the most pristine marshes in the upper basin. We conducted an experimental burn back in 1994 on about 650 acres. We had transects that we established in stands of mixed sawgrass and cattail, and pre-burn sampling was conducted just prior to the burn. So you can see sites 2 and 6 in the red, those were the burn sites, and site 10 in the green was the control site. But because of the similarity in the responses of the burn sites, I'm just going to show you the data from the site 2. We studied the long-term effects for 4 years post-burn of a single prescribed fire on plant community dynamics. And later you'll see why it was so important that we monitored that long as opposed to just 1 or 2 years post-burn. And we examined several responses to the fire, but for this whirlwind tour, I'm going to focus on the changes of sawgrass and cattail densities. And I want to mention that during the 3rd year post-burn, our control site burned in a wildfire, which gave us the opportunity to see if the effect of the burn was similar to that of our planned prescription burn. So this graph depicts the density of cattail. If it's a blue column, it represents densities similar to pre-burn levels, and if the column is pink, it represents densities that were significantly higher than pre-burn levels. So this shows the prescribed burn event, and we can see a dramatic increase of cattail for 2 years post-fire, but a return to pre-burn levels in the 3rd and 4th years post-burn. And this is where I want to point out the importance of the duration of the experiment. If we'd only monitored for 2 years post-burn, we'd have been alarmed at the magnification of the cattail invasion as a result of the burn. So this may have caused us to become quite conservative in our approach to using prescribed burning in these marshes. But because we monitored longer, we became less concerned because this was just the negative impacts were just temporary. However, since this is one of our most pristine marshes in the upper basin, it may be that the trend we see here would not occur in marshes that have higher nutrient levels, where the cattail recovery could take longer, or it may not occur at all. Well, what happened to the sawgrass as a result of the burn? At Site 2, sawgrass density was not different between pre-burn and 1 and 2 years post-burn, but we did see in the 3rd year a significant increase in sawgrass density, and that coincided with the decline in cattail density. Sawgrass density then declined in the 4th year post-burn. So once again, this trend would not have been detected had we terminated sampling after the 2 years post-burn. At the control site, there was no difference in cattail density for 3 years. However, when the control site burned in a wildfire, there was an increase in cattail density at 15 months after the fire, similar to what we saw at the original burn sites. However, in contrast, the cattail density declined here more quickly, and it was back to pre-burn levels by 27 months post-burn. Sawgrass trends not as obviously linked to the burn event as cattail density at the control site. Density was stable for 2 years, but increased prior to the wildfire. We may have seen these natural fluctuations in sawgrass at the original burn sites had we monitored those communities for several years in advance of the burn. But 15 and 27 months after the burn, sawgrass density returned to pre-burn levels. So in summary, we found that this fire resulted in a dramatic increase in cattail density. However, long-term monitoring revealed that the impacts were temporary. On the other hand, sawgrass was relatively unaffected by the burn, and overall we didn't see any major species composition changes as a result of the burn, and we confirmed that we could use prescription fire as a management tool, at least in a pristine wetland like blue cypress, to manage the marsh without fear of that sustained cattail expansion. My next project is in the same location in the upper basin in the blue cypress marsh, and an area just south of that called the Fort Drum Marsh Conservation Area. And again, it involves sawgrass, not cattail, and it's a sawgrass story that really starts out kind of sad, but it has a happy ending ultimately. So beginning in 1999, a sawgrass dieback event was observed in the marshes of the upper basin on one of our routine aerial reconnaissance flights. As you can see from this photograph of Fort Drum, the coverage of the dieback was quite extensive and easily identifiable on aerial images. Using low-level aerial images, we monitored and mapped the extent of the sawgrass dieback in Fort Drum and in blue cypress. So these maps show the healthy sawgrass in tan and the unhealthy sawgrass in red. And notice that these unhealthy patches seem to be along the edges of the sawgrass habitat, and a greater proportion of sawgrass was unhealthy in Fort Drum than in blue cypress. We also monitored the dieback on the ground. This graph shows a trajectory of the recovery in the unhealthy patches from that sampling effort. So Fort Drum is shown in the blue columns and blue cypress in the purple columns. At the beginning of the study in 2001, Fort Drum had far less live sawgrass cover in those unhealthy patches than blue cypress. And for Fort Drum, live sawgrass cover continued to decline. But sawgrass and blue cypress started showing recovery and reached about 55% cover in 2003. However, when we revisited these sites in 2007, look at what happened. Fort Drum had a surprising recovery that exceeded that in the blue cypress plots, and both of these sites partially recovered, albeit Fort Drum more slowly than blue cypress. However, when you put sawgrass cover on a 100% scale and you compare it to the cover of sawgrass in those healthy patches in the green columns, the story really isn't as rosy as we thought. Sawgrass cover in the unhealthy patches was about 50% in 2007, but the cover in the healthy patches was 100%. So the take home is that even though there was recovery, it was not to pre-impact levels as evidenced by the cover in the unimpacted patches. So we considered potential causes of the die-off. We ruled out insect damage, fungal infection, and rainfall since it measured at average levels around the years beforehand. But when we looked at water levels as a causal factor, we found that Fort Drum and blue cypress experienced vastly different inundation frequencies and depths. For the 5 years preceding the dieback event, Fort Drum was inundated 100% of the time, whereas blue cypress, just north of that, was inundated far less. Not only was Fort Drum inundated longer, it was much, much deeper, with water depths between 3 to 5 feet as opposed to just a half to 1.5 feet in blue cypress. And I tell you this to show you that this dieback happened under a wide range of hydrologic conditions. However, sawgrass generally tolerates dry conditions better than those extremely wet conditions. So this might partially explain why there was quicker recovery of sawgrass in blue cypress than in Fort Drum, and also that the dieback generally occurred at the edges of the sawgrass communities, where those areas may represent less than optimal hydrologic conditions for sawgrass. And then jumping ahead, maybe because these areas were wetter, they had far less than ideal fire return intervals for sawgrass to maintain dominance. So what about fire regimes? I'm going to show you a couple of maps, and you'll probably be able to discern this visually for yourself. This shows the fires that occurred from 1993 to 2001. So the brighter red, the more it burned. Now let's reveal the sawgrass dieback areas in yellow. And you'll probably notice that the yellow areas don't really seem to overlap the areas that burned. So let's look at the numbers. Let's look at this spatially. This graph shows the number of fires that occurred during that time and the spatial extent of unhealthy and healthy sawgrass and blue cypress. So the red portions of the bars are the areas with dieback, and the tan portions are areas with healthy sawgrass. And you can see that there is no dieback in areas where there are 3 or 4 burns, and increasingly more dieback that occurs with fewer to no fires. The same trend occurs in Fort Drum, except that it's truncated to only 0 or 1 fire, and we can see the sawgrass dieback only occurred in areas that didn't burn. This is pretty convincing evidence that precedent fire history is related to the spatial distribution of dieback. So how do we apply this information? Well, we looked at using fire as a recovery tool in an area just downstream called Three Forks Marsh Conservation Area. This aerial shows what the study site looked like in 2004. We had 5 quadrats on the north side that were burned and 5 on the south side that were left unburned to serve as controls. And then 3 years later, we conducted a second prescribed fire on both the north and the south side to show a once and twice burned treatment. So this is where it gets really exciting. At the beginning of the study, there was no difference between the 2 sets of quadrats on the north and south side of the transect. 1 and 2 years after the first prescribed fire, live sawgrass cover increased in the burned quadrats on the north side and decreased in the unburned quadrats. But in March of 2006, when we burned both of the quadrats, that resulted in an increase in cover in all the quadrats, and there was no difference between quadrats that had been burned once or twice. Notice too that the sawgrass had about 85% cover. And since a picture is worth 1,000 words, I'm going to show you what these dieback sites look like on the ground. This is site 1 on the north side before the first burn in 2003, and that palm tree is circled for a frame of reference for you. This is 1 year post-burn, and you can see that the litter is gone and sparse sawgrass is rejuvenated. Sawgrass is getting bigger and thicker by the 2nd year post-burn. And after this, remember, there's a second burn in 2006. And by 2007, there is an incredible response by the sawgrass that's quite dense and tall. So what are the take-home points that I want you to remember about the sawgrass saga? Precedent fire history was one of the most compelling causal factors where sawgrass dieback had a greater probability of occurring in areas that burned less frequently. The absence of fire and prolonged deep inundation can have a synergistic and negative effect on sawgrass. Partial recovery of sawgrass can occur in the absence of fire. However, that occurs slowly and it only occurs to about 50% of its cover. Also, prescription burning and maintaining the appropriate fire frequency of about 3 to 5 years can not only prevent dieback, but it can also promote recovery to pre-impact coverage. So next I'd like to talk about some more recent work to manage Carolina willow with chemical applications in the upper basin. Carolina willow is a native shrub in Florida, and it occurs where there are short hydro periods and on organic soil. Willow reproduces by seed or vegetatively. Growth is quite rapid, and those seedlings, they can outpace the rising summer water levels. They can survive and quickly grow into mature trees. Once they're mature, trees can tolerate a number of conditions that many other plants cannot tolerate. It's these efficient reproductive and establishment strategies that have allowed willow to replace historically dominant herbaceous marshes in the upper basin. In fact, over the last 4 decades, there has been widespread expansion of Carolina willow. This map shows the St. John's Marsh Conservation Area and the chronosequence of willow invasion. And from 1989 to 2009, the distribution of shrub swamp more than doubled and covered approximately half of the conservation area within 20 years. The primary reason for that invasion is because of changes in hydrology, specifically reduction of flooding duration and water depth, and secondarily, a reduction in the burning interval and nutrient enrichment and other factors that may have enhanced willow encroachment and establishment. So to deal with this issue, we have a number of tools in our toolbox. And one of those is prescribed fire, which we've talked about, and that's a natural and important driver in these wetlands. However, we found that mature willow is not especially flammable because it has high water holding capacity, which limits our ability to use this tool effectively. Another method to remove dense willow stands that we experimented with is mechanical clearing, and when combined with right hydrologic conditions afterwards was shown to be quite effective. However, mechanical clearing is quite costly and access is extremely limited due to the organic nature of the soils where willows grow. Which leads us to this project's focus, which is using herbicides to manage willow. Experimental willow herbicide treatments in the St. John's started with a study by UF in 2005, where researchers looked at the impact of several herbicides for 2 years post-treatment. They saw a positive impact using imazapyr, so we decided to use that herbicide to do a longer-term study where we monitored for 6 years. We selected 2 sites, the Sweetwater site and the C40 site, to maximize variation between the 2 sites with regards to willow canopy, understory species composition, and hydrologic conditions. The Sweetwater site was wetter and flooded 76% of the time, whereas the C40 site was drier and only flooded 21% of the time. We had 3 treatments at each site. We had a control, an herbicide A, which was ecomazapyr at a lower application rate, and herbicide B, which was a stronger mixture of ecomazapyr and glyphosate at higher application rates. And we applied the herbicides in the July of 2015. In this study, we used 1 meter square quadrats for ground cover characterization, and we estimated canopy cover by taking photographs skyward using an iPad camera. This graph shows the willow canopy cover for pre-treatment in 2015 in the green columns and 6 years post-treatment to 2021 at the C40 site. So while average canopy cover remained above 60% in the control, in the herbicide treatments it was completely eliminated for the first 4 years post-treatment. But by the 6th year post-treatment, we see a tiny bit of willow cover, averaging less than 5% in the herbicide B treatment. We see a similar story at the Sweetwater site, with all the plots having at least 50% cover before the treatment and the control plots maintaining that cover over the course of the experiment. After herbicide application, the treatment plots had no significant willow cover from 2016 to 2019, but there was recovery in herbicide A treatment to 20% cover in 2021. So for a pictorial journey on the ground changes, it's really impactful. You can see the understory at Sweetwater. This is one of the herbicide B treatment plots. You can see healthy canopy pre-treatment. The next year shows the dead willow, which degrades and decomposes over the years. And by 2019 and 2021, there's enough graminoid cover to carry a prescription burn that occurred in March of 2021, restoring the pyric nature of the marsh. So now moving from an experimental research to application in a management context, once we gathered information on the success of our experimental treatments, we began to implement treatments on a larger scale. This is a 2,100 acre treatment with a imazapyr just north of the C40 site. The aerial photos on the top show the area about a year post-treatment, and the bottom photos show the area after a wildfire in March of 2017. And you can see the area right of the channel that was herbicided and burned is now herbaceous marsh, while the untreated area to the left of the channel is still dominated by willow. And then a closer look on the ground shows you that we transformed this area from a willow swamp back to herbaceous marsh. So finally, if we revisit the maps of shrub encroachment that I showed you earlier, we can see that our treatments, especially in the northern section, resulted in a drastic reduction in willow swamp between 2009 and 2016, which was a whopping 36%. So in conclusion, we have several tools in our toolbox for managing willow. Where we can't use prescribed fire or mechanical control, we have successfully used herbicides to reduce the cover of willow for at least 6 years post-treatment. However, continued control in the long term without further herbicide treatments will mean we need to fix the issues that cause the problem in the first place, and that is hydrologic regimes and fire intervals. And finally, we'll continue to study ways to manage willow with different herbicides that have maximum impact on the willow but minimum off-target effects. So now I'd like to switch to something a little less researchy and tell you about a project to stabilize the L77 West levee shoreline. For this project, I'll talk about working across departments at the district, securing permits to plant, working with a contractor to install plants, and collaborating with other agencies to harvest plants and get advice. The L77 West levee is located to the Blue Cypress Marsh, which we've talked about before. And for this project, Environmental Sciences, where I work, got to team up with the district's Operations and Management Bureau to combine living systems or green infrastructure with their gray infrastructure, like using riprap to help solve a problem with levee erosion. 2 years prior to this work on the L77 levee, inspections by the Army Corps of Engineers indicated several locations along 2 miles of the levee, see those red dots, where there were erosion issues. The erosion averaged about 1 to 2 feet in height. However, some locations had up to about 3 feet of erosion. We believe that the erosion was due to wave action from boat wakes and wind fetch across the open water area, and potentially vegetation management with mowing and herbicide treatments along the levee shoreline. The overall goal was to establish native wetland plants along the levee to reduce the shoreline erosion by protecting the levee from wave action and stabilizing the soil by establishing rooted plants. To prepare the levee for the project, we informed the public of the project through social media. We placed signs at the boat ramp and installed buoys 300 feet from the levee to reduce boat traffic and wave action. We regraded and placed sod on the levee to keep erosion down before our plants were installed. We crafted our planting design to incorporate the hydrologic tolerances of each species and got advice from colleagues who had successfully planted these species in other areas. So this design shows a cross-sectional view of the plan, which was to plant spartina at the toe of the levee, flags and bulrush waterward of that, and then spatterdock in the 3 to 4 foot deep areas. And this drawing, along with others, were submitted with the permits needed for this project. We submitted our permit applications to the Florida Department of Environmental Protection to get approval for the planting project within 5 months. And our application was approved just in the nick of time, and we received our state 404 permit to do the project. The contractor was responsible for getting the permit to wild harvest and transport plants to the site. We coordinated with the Fish and Wildlife Commission and harvested plants from a nearby conservation area because the plants were plentiful there and they were free. The contractor had a large crew that was harvesting spatterdock, bulrush, and flags, including thalia. Spatterdock was installed using concrete blocks and planted on 5-foot centers. We installed bulrush on tighter 1-foot by 2-foot centers. Thalia and spartina were also installed on tighter centers, and this is what it looked like before and after that planting. And then this is just a closer look. I just want to mention documentation and reporting, which is so important in a project like this. Together with the contractor, we documented how many plants were harvested, did some spot check counts of the bags before installation, we tracked dislodged plants, and we estimated survival at the end of 30 days. So let's talk about overall survival. We had a criterion of 80% survival after 30 days for all plants. We found the highest survival in thalia at 84% and spartina at 83%. So yay for that. This shows the growth and establishment of thalia at the 450 station, which was about midpoint along the levee. And the plants were even flowering and looking good just 3 months later. Now the bad news. Bulrush and spatterdock had very low survival at 14% and 31%. The factors we believe negatively impacted the spatterdock and bulrush were constantly battering waves and lots of high wind storms and being overtopped by floating vegetation, especially the bulrush. Because not all species met the 80% survival criteria, the contractor had to replant. But since spatterdock had such low survival and it was most expensive species to plant, we opted to have them plant thalia because it had such high survival, and we put bulrush in areas with fewer floating weeds. Again, the main goal of this project was to reduce erosion. So this shows the 2,100-foot station before and after we planted thalia and bulrush. And then here it is surviving well in June, a month later. I do want to mention there was prolific recruitment of other vegetation that was becoming rooted along the levee, like cattail and phragmites and other grasses. And I couldn't find a single area that was showing erosion with all that vegetation there. And when the levee inspections were performed by the Army Corps of Engineers last November, just look at the improvement in the number of locations indicated with red dots. We went from nearly 2 miles of levee with erosion, and now we're just down to 2 red dots. So the project really was a success. So here are some lessons learned from our project, which I won't read out to you. We've kind of discussed these. But our operations and management staff are really excited about using this method to stabilize the shoreline along other levees experiencing erosion in the district. And that enables staff to work on other issues and projects. So now let's move to a project that involves wetland restoration on a much larger scale. In the Upper Basin, beginning in the 1900s, the historic floodplain suffered extensive alterations, and there was a drastic loss of wetlands. By 1972, 62% of the 100-year floodplain had been diked, drained, and converted to agriculture. In the Upper Basin, wetlands have been impacted by agricultural development. Loss of wetlands occurred due to changes in hydro patterns that changed the delivery of water to these ecosystems, and to changes in fire regimes due to the fragmentation of the landscape, nutrient enrichment from point and non-point sources, colonization of invasive plants, both native and non-native animal species, and finally, more recently, with the wetlands in the Upper Basin are being affected by the impacts of climate change, with changing water availability, weather patterns, and species distributions. So responding to the negative impacts that development had on the ecosystem, the district and all its many partners decided to restore or rehabilitate the floodplain of the Upper Basin starting in 1977. So how did we go about restoring the impacted wetlands? This map shows all 18 of our separate project areas in the Upper Basin, and this map shows 11 of those areas that were restored in red. These restoration areas ranged in size from 200 acres to over 14,000 acres. And you may know that the most important component of restoring a wetland is bringing back the water. So without the proper hydrology, we can't restore cattle pastures back to functioning wetlands. So getting the hydrology right is of paramount concern as the driver of all functions in these wetlands. To walk you through the process of floodplain restoration, I'm going to use one of our larger restoration areas known as Moccasin Island Project. This project area was converted to cattle pasture in the late 1960s. The effort to restore wetlands in this area was a joint project between the district and the USDA Natural Resources Conservation Service. It was initiated in 1999 and it cost $1.3 million. The objectives of this restoration were to reestablish the natural hydrologic regime, to encourage colonization and establishment of native wetland plants, to enhance habitat for wading birds and other wetland-dependent wildlife, and to improve water quality to meet background levels in the receiving marsh. So we took a three-phase approach to restoration to reach these objectives. Phase 1 involved the removal of agricultural infrastructure and the remediation of any contamination from past agricultural practices. And our aim was to allow the free exchange of water inside the property and to allow for water level manipulations needed for Phase 2. Phase 2 involved reflooding and maintenance of shallow water levels to encourage growth of wetland plants from the remnant seed bank in the soil. Wetland plants recolonize the site, and plant species typical of improved pasture like you see here were gradually replaced by wetland species such as pickerel weed, smartweed, and sand cordgrass. During Phase 2, we also planted 6 native plant species on a total of 55 acres, which included sawgrass and spikerush. And looking at the dates on the photographs, you can see the success of the planting just 1 year afterwards. To enhance landscape diversity of the area, we created a forested island, which is expected to enhance habitat for birds, as well as alligators and turtles. This island was constructed from a levee remnant and surrounded by a moat of deeper water on all sides to protect bird nests from land-based predators. Altogether, we planted about 400 trees of 15 native species, and we constructed 4 artificial snags to encourage bird perching and deposition of seeds to enhance plant diversity on the island. In Phase 2, we also monitored water quality to assess whether the water was clean enough, it had low enough nutrients, especially phosphorus, to reconnect the restoration area to the adjacent marsh. And we saw water quality improvement with a decreasing trend in total phosphorus, and by 2009, total phosphorus in Moccasin Island declined to a concentration which would meet the benchmark to reconnect this area to the unimpacted floodplain. The implementation of Phase 2, or the final phase, was hydrologic reconnection, which we did simply by pushing this elevated levee back into the adjacent canal to restore a more natural hydrologic regime on the property and reestablish the connection with the outside floodplain. So this shows you an aerial view of Moccasin Island and the process of levee demolition in April of 2009. Notice Mud Lake. And just 4 months later, we can see that Moccasin Island what it looked like after hydrologic reconnection. This shows a chronology of what Moccasin Island looked like before the wetlands were converted in 1940s, the pasture before restoration in the year 2000, and then after restoration in 2009. So take note that the complete restoration of this area, all 3 phases, was accomplished in 10 years after starting the project. But now, Moccasin Island has become an integral part of the Upper St. Johns River Basin floodplain. And as a result of our restoration, wildlife has become more diverse and abundant. Notice the bald eagle perching on our artificial snags we constructed on the island, and the Florida sandhill crane was nesting in the spikerush we planted. So we use this 3-phased approach to restoration on most of our restoration properties in the Upper Basin, and we finished our last restoration project in 2017. We've seen projects about sawgrass, cattail, willow, shoreline stabilization, and wetland restoration. But the most important thing that we need to think about with managing wetlands is what? And there's a hint in this title. Hydrology. To protect and restore the wetlands, we must focus on the single most important ecosystem driver in wetlands, and that is hydrology. Our hydrologic goal is to restore the natural attributes of the hydrologic regime, which includes both wet periods and dry periods, and the seasonality with which that happens. So let's look at a few challenges we've had with getting the water right in 3 large marsh conservation areas in the Upper Basin. All 3 areas are fully or partially contained by levees, and for a variety of reasons, some of these areas have been too wet, too dry, or maybe just about right. And I'll start with Fort Drum at the southern end. This is a hydrograph of the water levels in Fort Drum spanning from 1942 to 2016. And the main point I want you to notice is the red line ramping up to show that because of poor water flow under State Road 60 and after the L79 levee construction in the 1990s, the marsh was more deeply inundated for longer periods of time, with an average annual depth 1.2 feet higher than historical. And that long-term inundation in Fort Drum had impacts. This shows a series of surveys that we compared to find that the elevation of the marsh had changed. So can you guess in what direction? Was it higher or lower in elevation? These 2 maps show 2 surveys from 1983 and then a comparative survey in 2007. And looking at the elevation contours, you can see that the elevations increased with more tan color and less green across the shaded area on the map on the right side from 2007. If we compare the stage area curves for that area, we can see an increase in elevation of about 0.8 feet over 24 years. So deep and prolonged inundation resulted in plant community shifts, soil accretion, and loss in flood storage capacity in Fort Drum. And once we recognized this, we addressed it by adding a new culvert in the northeast corner of the property to allow for improved water levels in Fort Drum. In contrast, the St. John's Marsh Conservation Area has been too dry. This area is a challenge to keep wet because it has the biggest elevation drop along the entire 300-mile river, and the area is bounded by large drainage canals on either side. And when vegetation jams were removed just downstream in Lake Washington in the 1950s, it lowered the water elevation in the St. John's Marsh Conservation Area by nearly 2.5 feet. This caused an enormous loss of soil. In our elevation change analysis between 2000 and 2009, we found that the St. John's Marsh experienced soil oxidation and land subsidence where the maximum loss was 1 foot, shown in the dark orange, although some areas did experience a gain or soil accretion of up to 1 foot, shown in the light green. But if we look at the gains and losses on a per acre basis, we can see that the loss of soil far outweighs the gains, and overall we lost over 2 million cubic yards of soil. That's a total of 275,000 dump trucks over the 9-year period. The hydrologic alterations in St. John's result in a tremendous loss of soil, a shift in the plant community from herbaceous to shrubby, increased nutrient loading for phosphorus and nitrogen, and increased evapotranspiration and carbon dioxide emission. If we compare Fort Drum to St. John's, we can see a gain of 98 dump trucks of soil each day in Fort Drum, compared to a loss of 84 dump trucks worth of soil in just 1 day in St. John's Marsh Conservation Area. So just imagine nearly 100 dump trucks rumbling past your house every single day, either bringing in or taking out that much soil. These wetland processes may seem slow and obscure, but they can have large cumulative effects on flood storage and environmental conditions. So what does this mean for the blue cypress marsh? That's maybe just right. Seeing the changes that we witnessed in Fort Drum and St. John's, we were concerned that there may be elevation changes in blue cypress as well. We performed surveys in 1993 and 1996, so we have a good idea of the historical ground elevations in blue cypress. However, our hydrologic data indicates that we could have an issue. From 1993 to 2023, the mean annual water elevation in blue cypress marsh was below the average marsh elevation about 65% of the time, indicating that dry marsh conditions could result in soil oxidation and lowering ground elevations like we saw in St. John's. As we speak, we have a new survey being conducted in Blue Cypress to measure the current elevations so we can assess the change, if there is one, over those 30+ years. So how many dump trucks will be coming in or going out from Blue Cypress each day? That remains to be seen. For a final wrap up with hydrology, I showed you 3 different hydrologic issues in Fort Drum, St. John's, and Blue Cypress, as well as approaches to investigate those issues using the topographic surveys, and results from those investigations showing increased or decreased elevations. But what about application? How do we know what the appropriate hydrology is to manage each of these areas? To determine the appropriate hydrology for each conservation area, we developed environmental hydrologic criteria, or targets, that incorporate the extreme highs and lows, the extended flooding and drying periods, as well as seasonal variability. Or put more simply, we identify criteria that determines the optimal conditions for how deep, how often, how long, when, and how quickly water levels change. But if the marsh surface has changed or lowered, you can see how that would change our numerical criteria. We set elevations using the stage area curve for 3 critical elevations, the upper, central, and lower critical elevations. That's why the elevation data is key in managing hydrology. If our ground elevation is changed, we will be managing water to meet the wrong water levels. When we compile all of the EHC, environmental hydrologic criteria, we have several targets that we hope to achieve on a long-term basis for each of our project areas. In this table, I color-coded the criteria based on what the primary goal is meant to protect or prevent, whether it's to protect fish, snail kites, or other wildlife, maintain emergent plant communities, prevent soil oxidation, or prevent willow invasion. We regularly monitor our project performance for these criteria, and on this table, if we're meeting the criteria, the box is green, and if we're not, the box is red. So overall, we see more green than red, and that's a good thing. In Fort Drum, we are meeting all the criteria except the desirable drying criteria because it's been too wet. In Blue Cypress, we are meeting 6 out of 8 of the criteria, and I mentioned it was quite dry for many years, so we did not meet the inundation frequency criteria that might have caused some soil oxidation, and we're not meeting the seasonality criteria for willow prevention. And then finally, in St. John's Marsh Conservation Area, we are having the most challenging time because we're not meeting half of the criteria. And we know that this area is too dry and that soils are subsiding and willow is expanding. And this is why we believe it's important to address that by making structural changes to rehydrate that marsh. But what these environmental hydro criteria do for us is give us a measurable way to track our success and challenges in fulfilling the district's 4th core mission to protect those natural ecosystems. So this has just been a snippet of all the amazing things I've had the privilege to work on at the district over the past 35 years. Hopefully you've seen something that piques your interest. However, there are many wetland and water resource related jobs at the district. Interestingly, I found this on our district website listing all the reasons you should work with us. And I'd be happy to answer any of your questions about working with the district at our roundtable discussion following this. There are so many wonderful reasons to work at the Water Management District. We see interesting plants, amazing and sometimes scary animals, and the vehicles. This is one of the most fun parts. Airboats, ATVs, tracked vehicles, trucks, bulldozers, oh my. But the absolutely best part of working at the district is all the amazing colleagues and friends that I've made throughout the years. With that, I thank you for your attention, and I hope that you have enjoyed this whirlwind tour of wetland work at the Water Management District.